picking up where the previous video left off, we are going to include a whole lot of vocabulary in our discussion today. And yes, a lot of this is something that you could just read on your own and study it, but sometimes it helps to hear someone talk it out with you guys. So today's video is going to cover how we classify matter. We are also going to cover specific heat and thermochemistry and energy changes with matter, which is the small portion of math that you're going to include in this unit. So follow along with us. We're starting right where the last video left off in your notes. If you are starting with this video, then you can find links to the notes and the slides that we are lining up with just below this video. So here we go. Heterogeneous matter, or I have heard people pronounce it heterogeneous, okay? I sometimes get a little bit of spice from other people for saying that. Heterogeneous, heterogeneous, to me, it doesn't freaking matter. But hey, break down the words into the word parts, and you see hetero. And you've seen hetero in other words, and hetero simply means different, not the same. And so matter that has parts with different properties. And what this is going to apply to here in a second is we're going to classify certain combinations of ingredients as mixtures. And so we are going to be able to classify certain mixtures as heterogeneous or heterogeneous. Some examples: sand and water. If you're ever at the beach, where's the sand? The sand settles to the bottom of the water, correct? I don't really like seeing iced tea here because, listen, I consider myself an avid iced tea drinker. Look what we got right here. Little McAllisters, okay? Good iced tea is not heterogeneous, not heterogeneous. Heck no. Good iced tea, every sip is the freaking same, and I don't want any crumbly bits in any of my sips. Absolutely not. Now, if you're getting Gold Peak, then sure, you got some gross stuff in there. Don't drink Gold Peak, people. Good Lord. Concrete. If you've ever done a sick ollie on your skateboard and you face planted on the street in front of your house when your eyes are really close to the pavement, well, then you can see there's some black specks, some gray specks, some white specks. It's obviously not the same material all throughout. So there's definitely, depending on where you zoom in, you're going to see different substances there. And granite. Oh, my goodness. The stuff that makes your countertops look so elegant. Oh, my God. The mica, the quartz, the feldspar. Different colors all throughout to add to the spiciness of your countertop. My goodness, I could serve some charcuterie on that. Woo! So, where there is, of course, heterogeneous or heterogeneous, of course, there's homogeneous or homogeneous. Oh my goodness. Correction on the spot. Boom! Homogeneous or homogeneous matter has similar properties throughout the substance, aka the mixtures that we're going to be talking about here in a second. Every way that you look at it, it looks the same. The top is the same as the bottom, the left is the same as the right. If I zoom in on one area, zoom in on another area, they look the exact same. And so, before we start talking about mixtures, let's just talk about individual substances here. Sugar. If I buy a bag of sugar, I certainly hope that every grain within it is a grain of sugar. I hope that some dealer from the bad side of town hasn't slipped something in suspect in the bag that looks similar but is not the same substance. No, when I spend $1.46 on a bag of sugar, I expect to get all sugar. Same with my salt. Gold. If you're buying 24 karat gold, every single atom within that block of metal is gold and is what you paid for. So hopefully you're not getting, hopefully you're not on the losing end of a deal when you're not buying, complete, total, pure gold. So now we finally get to talk about these mixtures. Okay, we get to talk about these mixtures here. And a mixture is composed of two or more materials. They each maintain their own characteristics. How is this different from what we talked about before? The other word you can relate this to is compound, which, if you recall, compound from the previous video was two or more elements together chemically bonded. Meaning no matter how strong you are, I can't reach in and pull them apart. In a mixture, they are not chemically bonded. They're only physically thrown together. Think of it in a mixing bowl, right? M&Ms and dough. Just mix them up together. I can easily reach in and pluck out the M&Ms. That is a mixture. And so now, how do we apply these terms that we just learned, heterogeneous or homogeneous? Well, does it look the same throughout? Is it evenly mixed? Does the top look like the bottom? Does the left look like the right? If it's a no, then it's heterogeneous. If it's a yes, then it's homogeneous. And another term for a homogeneous or homogeneous mixture is a solution. You will see people use that interchangeably. A solution is straight up just something dissolved in water. One of the most common examples, sugar in water. Let's say you're drinking lemonade or Kool-Aid, and obviously you have to dissolve some sugar in there. When you dissolve something, aka the solid that you've put into the water, disappears to your eyes, it is evenly mixing itself, evenly dispersing itself throughout that solution. So it is a homogeneous solution. Every sip should taste the same. Another version of a mixture is an alloy. If you're in the band, then you know a whole lot about alloys. If you play in the brass section, you especially do. If you're a jewelry aficionado, then some of your jewelry, rose gold, white gold, those are alloys. And what alloys are is they simply melt down multiple metals and they shape it into these new shapes and these new colors for you. It just gives different tones, right? White gold is typically a little bit of silver, a little bit of gold. Sometimes it's zinc and gold, anything that gives it that more silvery color. And then steel, as you can see right here, Minecraft got it right. A little bit of iron, a little bit of charcoal, you get that steel built, or other video games when they do that sort of thing. And then brass, as we were just talking about with the band section before, brass is copper and typically zinc as well. It gives it that more shiny luster to it. So now, what can we do with these mixtures? We've said that they can physically be separated, but what I'm thinking there is I can't reach in with my arms and pluck out every mixture I'm thinking of, right? I certainly can't reach into that solution we were just talking about and pull out all the sugar molecules. Absolutely not. Well, there's different techniques. When I say physically separate, it doesn't necessarily mean with your hands. Okay, there's different tools we can use here. Decanting is a real sloppy, real cheap method for when essentially a liquid and a solid form layers. Sand and water is the best example of this. If I let sand and water sit by itself, the sand is going to go to the bottom, the water is going to sit on the top. Well, what can I do? If I don't have machinery or tools in order to very cleanly separate it, I can very carefully pour the liquid off the top, and that's decanting. If you have a much more expensive set of equipment, that would be the centrifuge. The centrifuge is essentially a helicopter for test tubes, and cuvettes actually are what these things are called. Very, very small capsules where you can put very small amounts of sample in there, and what it does is it spins thousands of rotations per minute, and it separates substances on the smallest amount of density. If they're this far apart in density, it'll still separate them into layers. I remember a lab I did in college was you swab some of your cheek cells, so you're breaking open the animal cells, and you centrifuge it, and it actually separate it based on the organelles in those cells, ribosomes, mitochondria, that sort of thing. Very, very, very cool. Very expensive. Not going to see that in too many high schools. So hopefully if you go to a university after high school, hopefully they got a little more funding for you there. Filtration. Hopefully you've done some kind of filtering in your day. If not, you're definitely going to do it in the science lab. You just take filter paper and you pour in your mixture up the top. Your liquid, aka your filtrate, is going to go through, and whatever solid you're capturing up top is going to remain up top. It's too large to actually go through the filter paper. Vaporization is where you're going to evaporate whatever liquid that solid is trapped in, aka sugar and water. We could evaporate the water in order to get the sugar back. Just be careful not to burn the sugar. And another form of mixture separation, paper chromatography. Not something that we're going to do in high school typically. I never did it in high school, even through AP chemistry and all that. But it is something that you do in college. Very, very cool. Just not something that high school level labs typically do. So those are mixture separation techniques. Very, very cool. There's more beyond that, of course. And sometimes you can think very simply. Even taking a magnet to certain things is going to separate a lot of mixtures. So let's talk about things that aren't mixtures, pure substances. And we've actually talked about them already. Compounds, water. Water, what is its chemical formula? H2O. That is a compound. It's hydrogen and oxygen. It's not the same element. It's not just one element, and yet it is pure. Why? Because every individual component within that bottle of Ozarka water or Fiji water that you're sipping on, every molecule is the same. It is pure. I sure hope it is. That's what you're paying for, an outrageous amount of dollars for that $5 bottle of half a liter of water, of Fiji water. Are you kidding me? Compounds are pure. When I buy a bag of sugar, every single grain, every single molecule in there better be that sugar that I'm paying for. NaCl. When I'm buying a bag of salt, every single formula unit, every single grain better be salt. Compounds are pure, okay? Even though they are made of more than one element, compounds are pure, okay? Which leads us to our other pure substance. If the compounds are pure, then of course the elements that make them up are also pure. That 24 karat block of gold we were talking about not too long ago, that is pure gold. There's nothing else in there. Straight up, every atom in that block is gold. Okay, so those are your pure substances, compounds, and elements. Now let's talk about how we can classify these properties. Whenever we're analyzing and observing these substances, what can we say about them? Well, they have various properties. Extensive and intensive properties. These might not be words that you've heard before. An extensive property is a property about the substance that changes depending on the amount that you have. How big were you when you were born? On your birth certificate, it probably says how long you were, how much you weighed. Well, obviously, as you got a little bit bigger, therefore your height got a little bit taller, and your weight obviously went up. Your mass, your length changed. There's not too many more aside from that. But what about this McAllister's tea? As I'm sipping on it throughout this video. Ah, so smooth, right? This McAllister's tea. As I consume the tea and there's less in the cup, it's obviously occupying less space, therefore less volume. But there's not too many extensive properties beyond that. All of the other properties you can think of whenever you're observing a substance are intensive properties. Intensive properties are properties that do not change with the amount of substance that you have. And some of these might seem kind of out of the box for you. Density. How does density not change? Well, density, remember the mathematical formula for it is mass over volume. Meaning that if I've got more stuff, obviously it weighs more, but it's also taking more space. So when you increase the mass, you're also increasing the volume that it's taking up. Therefore, the density never changes. Density is one of the number one intensive properties you want to internalize. And this is why density is so cool. We can actually use it to identify unknown substances. If you can calculate its density, you can compare that to a table of density values and actually identify what the substance is for the most part. Ductility might be a new word for you. Ductility means you can draw it out into wire. You can stretch it really thin. That's what metals are really good for. If you were to crack open the walls in your house or your apartment, then you're going to see copper wiring most likely. And that's because metals are typically very ductile. Malleability, how malleable something is, that means it can be hammered into sheets, essentially can be molded into different shapes. And then color and melting point. Color does not change with the amount of stuff that you have, right? Look at your hair. If you were to pluck out a singular hair, it's most likely going to be the same color. Yes, you might have a few gray hairs in there. I definitely don't. I'm going to stay a luscious brunette for the rest of my life. But if you pluck out an individual hair, it's probably going to be the same color as the rest of the hairs, right? Less hair, same color. And then melting point. Oh my goodness. And of course, there's more intensive properties beyond this list right here. But melting point, how does that not change? If I throw an ice cube and a glacier in my front yard, of course the ice cube is going to melt faster, right? But that's not because the melting point is different. That's simply because there's more water in the glacier to melt. Therefore, it's going to take longer for that water to melt. Yes, water freezes at 32 degrees Fahrenheit, 0 degrees Celsius. It also melts at that temperature. It's just going to take longer to melt more of that ice. So the melting point does not change in a substance. That's an intensive property. Let's think of a few others. How toxic something is. Yes, if I ingest a lot of toxic stuff, I'm more likely to die. But that doesn't change the fact that it is toxic. Toxicity is an intensive property. What about flammability or combustibility? The ability for something to explode or catch on fire. If I've got a little schmeckle of gunpowder versus an entire barrel of gunpowder, and you see in the movies, they blow it up. Well, of course, the barrel is going to blow up bigger, but that's not what we're asking. We're talking about the property of whether or not it can blow up, not the size of the boom. We're talking about whether or not it can blow up, which is why those are intensive properties, okay? Types of properties that matter. Now we're looking at the physical versus the chemical side of reactions and substances that we're looking at in the lab. Physical properties, anything that you can assess about a substance without actually changing it. Because if you are involving yourself in a chemical reaction, you are changing something about that substance in front of you. It is not going to be the same substance that you started with. And physical properties can be measured or observed without changing it. So examples, you can think of a ton of them. Color, whether or not it dissolves, I can just plunk it in water. Dissolving it does not change the substance. I can boil the water away and get the substance back. The substance does not change. I can put it on a scale to get its mass. I can knock on it to figure out its hardness. I can sniff it to get its odor. All of these things are not changing the chemical identity of the substance. And that is the key to physical properties. If we look at chemical properties, something about it is going to change. That combustibility, that flammability that we just talked about. Can you get that gunpowder back after it goes boom? Absolutely not. It went boom. It's no longer powder in your hands, right? It has obviously undergone some sort of chemical reaction and created something new. So, chemical properties the substance is going to undergo a chemical reaction and it's going to form a new substance or new substances, can form multiple substances. So really the main thing that we're looking for here is what are the evidence of chemical changes? And I remember we learned some of these way back in elementary school. I remember talking about them in second grade, right? You put Alka-Seltzer in water and you see the bubbles, right? The bubbles being formed. Bubbles means chemical change. Well, really, the real thing that you're looking at here is the bubbles are a gas being formed, a gas that was not present at the beginning. If the color changes, and I don't mean dropping food dye into a cup of water, that's not color change. I mean you take two crystal clear things together and you put it together and it turns yellow. Now that is a color change. Change in temperature. That doesn't mean putting it over a stove and it gets hot. Duh. I mean you take two room temperature things together and it gets scalding hot. Or it gets freezing cold. Some weird stuff, people. And then formation of a precipitate. Precipitate might be a new word for you. Precipitate is a solid formed out of a couple of liquids. Okay? It is a solid product that was not there in the beginning of a chemical reaction. So very, very important term there. A physical change is when we are going to change what a substance looks like, but we are not changing its chemical identity. Very, very, very important here. A phase change is not a physical change. Here we are. We're starting with a glacier in the old cold Arctic Circle, and the sun's beating down on it, melting this glacier into the ocean. Well, what is this ice? Ice is frozen water, people. Didn't know if you know that. H2O, and when it melts, it's still H2O. And then when the sun beats down on it and the water rises up to water heaven, evaporation, all that jazz, it's still water, people. Water vapor. A lot of kids get that. A lot of kids have that misconception. When I'm boiling water to make a nice hot bowl of spaghetti for the hot date that I got coming over, when you're boiling water, you are not literally separating the hydrogens from the oxygens. You are not. What you are doing is you are actually separating waters from waters. The water are attracted to each other. Water molecules are attracted to each other. And when you boil it, you're actually separating the water molecules from each other. But the bond within a water molecule, between the H's and the O's, is so strong that just putting it over a stove is not going to be strong enough to do that, okay? So when you boil something, when it goes from liquid to gas, it is not a chemical change. It is only a physical change. None of the phase changes are chemical changes. All of the phase changes are physical changes. A chemical change, though, is going to result in a new substance, and this is going to present itself in the form of a chemical reaction. And you've probably seen some of these. You might not have written any before, but you're going to get a whole lot comfortable with it in this class, in this course, okay? And we're going to show you an example here in just a second. But how it works is you're going to start the reaction with what is going to be reacted, aka the reactants. Man, it's a very logical name. And you are going to produce your products. It's amazing. And between the reactant side and the product side is an arrow, sort of simulating a before and after. Some reactions, it's got an arrow going both ways because some reactions are completely reversible. Most of the time, not the case. But we'll see examples of that in the future as well. And so, here's that precipitate word again. A solid that separates from a solution, aka you started with two liquids and you ended with a solid product on the other side. Very important word. It's something we're going to see frequently as well. So we started off with this limestone, and we smushed it up with a nice little mortar and pestle, and now it looks like this very conspicuous white powder that is certainly not narcotics in any way, but this is not changing the chemical identity. It is still CaCO3. It is still calcium carbonate, as we can see there. But we put it over heat, and oh my goodness, a gas is forming that was not there before. And if we were to assess the chemical identity of the powder in the base of this beaker here, it's not CaCO3 anymore. It's now CaO. Either way, it produced two new chemicals, two new substances that were not there before. And that is the key to a chemical change. Something else we need to know before we go into our quick rundown of the periodic table: conservation of mass. This is the all-telling law of chemistry. You're not a wizard. You simply aren't. If you are, please identify yourself now because we've got work to do. I've got plans, okay? But if you're not, if you're a standard old Joe, that's totally fine. So am I. Mass is neither created nor destroyed during a chemical reaction. You're on a hot date with the love of your life. She's agreed to watch some set of Marvel movies in your house that evening, and you decide to, show off your cooking ability. So you get a nice bag of popcorn ready, and it has 100 kernels of popcorn in there. How many pieces of popcorn can you possibly have at the end of the microwaving? No more than 100. If you somehow come back to the living room, the den, whatever you're watching it in, with 200 pieces of popcorn, you have created stuff that was not there previously. That's not possible, people. That's not possible. Unless Mr. Orville Redenbacher has mislabeled his container and you are fortunate enough to get twice as much popcorn as you paid for. Very lucky. It's just not possible. So, here we have a simulated reaction. A plus BC makes B plus AC. If I started with 50 grams of A and 50 grams of BC, I started with a total of 100 grams on the reactant side. So what's the total amount of grams I can end with on the product side? It can't be any more or less than what I actually started with. I made 70 grams of AC, so 70 of it is right here. Therefore, the other 30 must be in B. Maybe I can't see it. Maybe it is some gas like this CO2 on the screen right here. Maybe it flew off into the sky. But either way, those grams are still there. You didn't destroy anything. You did not create anything out of truly nothing. Unless you did. Which I said, please contact me. We've got work to do. Okay? So, let's pause there. And let's come back and let's talk about some properties of these substances. Now we're going to be talking about the different characteristics of the different types of elements on the periodic table. Then we're also going to take a short look at where these elements are located on the periodic table. That is not something that you can really, or that you really need to have a long conversation about, because every kid needs to label their own periodic table, okay? And yes, we'll point out where they are, but you can color code it the way you want to, label it the way you want to. Either way, metals. We've heard that word metals before, and a lot of the periodic table, a lot of the elements on the periodic table are metals. In fact, roughly 3/4 of the periodic table are metals. So 75% of those 118 elements are metals, and metals are very good at conducting electricity and heat, which is why if you're ever touching something metallic in the hot Texas summer, it's probably going to be pretty hot if it's outside. At room temperature, most are solids. There is an exception to that, and the main example is mercury, which is a liquid at room temperature. But some of you may have seen videos on an element called gallium, and gallium is super cool, and it can essentially become a liquid at room temperature. Very, very, very cool. And most metals are very malleable and ductile, as we stated before. Copper being one of the coolest examples of that, as it's in all of our walls, in our apartments and houses. Lots of electricity being run through that very ductile copper wire. Very, very, very cool. Most of them are silvery or grayish, they're shiny. And then they have very, very high melting points. Tungsten having the highest melting point out of all of them. Nonmetals are essentially the opposite of all of that. They're very poor conductors of heat and electricity. A lot of them are gases at room temperature, although there are solids, and there's also a liquid. Bromine is the liquid at room temperature. But there's not too many solids in the nonmetal category. A lot of them are gases. But if they are solids, they fall apart. I always imagine like birthday cake, essentially, without the icing on the top, just a cake that falls apart in your hands. And so you can't stretch them out into wires typically. And then there is a third category, metalloids, which are kind of the best of both worlds. Whereas metals were really good at conducting and nonmetals were really poor at conducting, metalloids are kind of good at conducting. And there's really only a few of these on the periodic table, and we'll point out where those are. And all of these are solids at room temperature, but they're kind of right in the middle. They don't conduct, they don't not conduct, they're not totally brittle, but they're not totally malleable like the metals are. So now let's look at the periodic table, which as I said, we're not going to take too much time on this. We can just point out how the periodic table is laid out. You can either look at the vertical columns, which are known as groups or families, or you can look at the horizontal rows, which are also known as periods or series. Okay? If you are in the same group, you are in the same family. Why do they call them families? Well, it's just like how you are with your family. You probably look a little like them. You probably behave a little like them. So elements in the same column behave similarly. That is why it is organized the way that it is. It is not randomly laid out. It is certainly not laid out in the order that they were discovered. it is about the properties of the elements. And so we are going to talk about that. Feel free to color it the way that you'd like to. It's totally up to you. Okay. Uh, First off, we're going to start with hydrogen, which is in the very top left of the periodic table. Hydrogen is kind of on his own. He is a non-metal. He is a gas. And yet, he's in a family of other metals because he behaves like this family of metals. So he's very, very unique and kind of on his own. And in that same column, although hydrogen is not included, are the alkaline metals, the most reactive metallic family. They're very, very soft. You can actually cut them with a butter knife. And if you chuck them in water, they all explode. They all react very violently. Very cool videos to be searched there. Moving on to the alkaline earth metals, which are group 2, a little less reactive than the alkali metals, but still quite reactive. Very, very cool. Very, very cool. Then the names get kind of boring for a while. We're going to look at this whole middle section, which are the transition metals, and they do not each get their own family name in those columns because they are kind of unique in the way that they all sort of behave on their own. In fact, the thing that they have in common with one another is that they're all kind of unpredictable. They kind of behave randomly, that sort of thing. And it's not random, so to speak, but it's not as consistent as the families on the outer groups of the periodic table, which are also known as the representative elements of the periodic table. So the transition elements are in the middle, and the representative elements are on the outside. Those are the main A block groups that we're looking at there. Then the names get kind of boring, as I said. Group 3A or Group 13 is known as the boron or the aluminum family. Next, as you can predict, arguably the most important element on the periodic table in the element of life, the carbon family, as carbon is the first element shown in this family. Then we go to the nitrogen family, as nitrogen is the first element pictured there. And then we get to the oxygen family, or the chalcogens, as you'll see them called. Chalcogens, very, very reactive, super, super important. They also stink. Oxygen doesn't really stink so much, but sulfur does, and the other elements in that group as well stink. And then we get to the most reactive group of nonmetals, the halogens, which is going to start with fluorine at the top of that family, going down. And then the far right family, you've probably heard of this one, they are known as the noble gases. And they are not the most reactive, even though they're on the opposite end for the alkali metals. And the reason why they're called the noble gases is because they don't need nobody. They're as happy as they can be. They're in their final form. They're stable, which is why they don't need nobody, which is why they don't need to react in the first places, which is why the halogens, the group that we just talked about a second ago, is actually the most reactive set of nonmetals. And then the very bottom two rows on your periodic table are known as the lanthanides and actinides, otherwise known as the intertransition metals. A lot of these guys are radioactive. They're very, very big elements, and they have various properties throughout them. Okay? Very, very cool. Not the topic of too many of our conversations in this course, though. Maybe a little bit later on in your chemistry careers. So now let's look at where these different types of elements are on the periodic table. Metals versus nonmetals versus metalloids. Boom! Red for metals, yellow for metalloids, blue for nonmetals. Look at all the metals. As we said before, it's roughly 3/4 of the periodic table. And something I would implore you, if you're not a coloring person, I'm not a coloring person. When I was in preschool, I never colored inside the lines. It's so boring to me. But something I would make note of is where this little staircase line is on everyone's periodic table, because that staircase line is the dividing border between the metals and the nonmetals. And all of the elements present on the staircase are your metalloids, the main ones that you're going to be looking at here. Yes, aluminum is on the staircase, technically, not a metalloid. Aluminum is a metal. Has some metalloid-esque tendencies, but definitely a metal, people. Okay? Our final topic of the day, thermochemistry, energy changes in matter. And this is the most exciting portion of this unit. I know it's been a lot of vocabulary up to this point. I am so sorry. I don't pick the curriculum, okay? I do as the great state of Texas commands me. I'm Texas's loyal servant, and I'm trying to spice it up as much as we can. But now there's no need to add any extra spice, any extra seasoning, because my goodness, this is where it gets hot, hot, hot. Okay? So just as there was a law of conservation of mass, there is a law of conservation of energy. Energy cannot be created nor destroyed. It can simply be transferred, and it can be exchanged for different types of energy throughout. And the main types of energy that we're talking about here is thermal energy, heat energy. And so, thermochemistry is the study of transfers of heat during physical and chemical changes. Sadly, we can't just stick a device in and determine the heat energy within a substance. Okay? Something we're going to talk about here now is, yes, we can assess the temperature of something. And what the temperature tells us is essentially the average kinetic energy of a particle. Based on the temperature, that's telling us how much energy these molecules and atoms are moving around with, how much kinetic energy they've got. But heat, the energy trapped within, is sort of a different measurement. But what we can assess is we can measure the energy that is transferred between substances. And we're going to utilize the temperature to do that, okay? So we can't directly assess the heat, but we can directly assess the heat transferred. And so, one of the first points you have to get into your head is heat will always travel from samples with higher temperatures to samples with lower temperatures. Always high to low, never the other way around. It's kind of like when you were taking biology last year and they talked about diffusion and osmosis, all those kinds of passive transport in the body. It always goes from high to low, high concentration to low concentration. Heat is the same way. And so you got to ask yourself something weird now. Oh my, how does my refrigerator actually work? I thought when I take this hot burger off the grill and I end up not being hungry, so I stick it in the fridge for later, I thought my fridge identifies it as a hot object and attacks it. But that would be the cold going to the hot. That's not the real story. The real story is actually a heartbreaking one, if you ask me. That burger bravely goes into your refrigerator. It looks all around, it assesses its surroundings, and it says, my goodness, this place, this desolate, freezing wasteland. What can we do? We got to make it hot in here. And what it does is it releases heat left and right, up and down. It gives it its all. It sacrifices its entire body to try to heat things up in there. But of course, the refrigerator, backed by the mechanism on the backside with a Freon dispensary, wins. There's a whole lot more ability to make things cold in there than one singular burger patty can emit in the form of heat. So the burger loses and drops to the refrigeration temperature and loses the battle. However, if you were to stick, hundreds upon hundreds of hot burger patties fresh off the grill in your refrigerator, it's possible your refrigerator would lose. It's possible. Who knows? Either way, that story, it gets to me. All right? So look at these little letters that we're seeing next to these terms we've talked about. Temperature, capital T, of course. Heat, kind of randomly a Q. I'm not too sure why it is Q. Q is commonly associated with energy, but if you're asking me, heat could have something else. You may also see delta H if you're looking online. Delta H is going to come into play a little bit later on in this this discussion. Delta H stands for change in enthalpy, which, yes, is the change in heat, but that does require a little bit of a different conversation if we're going to directly talk about enthalpy. So we'll save that for a little bit later on. Next, the amount of energy transferred between samples is dependent on what the heck is transferring and what the heck is absorbing, right? And this is what we're going to call specific heat, which is labeled with the letter C. The amount of energy required to raise 1 gram of substance by 1 degree Celsius. How easy is it to change the temperature of a substance? You're going for a jog in the hot Texas summer. I don't know why you're running, but you're crazy. And you come out into the field of your favorite park. It's 104 degrees outside. My goodness, you're drenched in sweat. There's a little bit of shade, okay? A little bit of shade down the trail. And just underneath the shade, you see 2 benches. One made out of a nice, delightful cedar. Nice cedar planks. And one made out of, basically, might as well be a cast iron skillet over here. Which do you choose to plant your cheeks upon to get just a moment of respite? If you said the cast iron skillet over here, you're dead wrong. You'd be scalding your cheeks within seconds. Look, the way that they designed this bench, it's as if they want you to have grill marks on your backside. No, of course not. You're going to plant your cheeks upon the cedar bench. Why? Because the cedar bench has a much, much higher specific heat. It takes more energy to raise the temperature of this bench than it does the metal. The metal is very, very good at absorbing heat. It's a great conductor of heat. That's what we talked about when we were talking about the elements on the periodic table. It's a very good conductor. The wood is not. So this has a lower specific heat. This has a higher specific heat. And now with all of these variables, we're going to get to the equation, the only math part of this unit, which is known as the formula for calorimetry, which does have its practical uses in the real world, of which we're going to discuss now. Here's your formula. If you're going into med school, well, then I'm sure you've heard of the MCAT. Sometimes we call this the MCAT formula. Q equals MC delta T. The amount of energy transferred is equal to the mass times the specific heat times the delta T. What the heck is a delta? This triangle. Let me tell you a little story here. I have a wife. This wife went to college. When this wife was in college, wasn't my wife back then, she was in a sorority. And that sorority was delta, delta, delta. Tri-delta. Well, what delta means is change. And let me tell you, I don't know if it was destiny or what, but she was the right fit for tri-delta. This woman is absolutely unpredictable. I don't know what kind of woman I'm going to get on Monday versus Tuesday versus Wednesday. You get the picture, okay? Change, change, change. Delta, delta, delta. Change, change, change. Unpredictable. My goodness. Love her, but my goodness. So anything attached to this delta symbol means change in whatever you're looking at here. Essentially final minus initial. So the energy transferred is equal to the mass of the substance that you're looking at times the specific heat times the change in temperature. Very simple formula. And how it's going to work is we're going to give you all of the variables except for one, and you solve for the last. So let's look at our units here. Mass is typically measured in grams, but you kind of have to watch out for that. Specific heat is typically in joules per gram times Kelvin or degrees Celsius. Doesn't really matter there. Because we're doing the delta temperature, the change in temperature, it doesn't matter if we're in Kelvin or Celsius because you're taking the raw change into account, not the temperature itself. So a 50-gram sample of an unknown metal is heated with 800 joules of energy. If the temperature of the metal increases by 41.6 degrees Celsius, what is the specific heat of the metal? So we're looking for C here. Grams is obviously mass, so that's the M, and the temperature increases by 41.6 degrees Celsius, so that is our delta T, this 800 joules of energy. Q energy is always measured in joules, not J-U-U-L-S as the kids would like to think with their lemon lime flavored clouds and all that, but no, this is J-O-U-L-E-S, different unit. Okay, that's the unit of energy that we're concerned with. So they're giving us everything that we need. They're giving us the Q, the M, and the delta T. We are simply looking for C. Let's solve it on the board.
Here we are solving out our calorimetry example problems present in your notes. There should be 3 examples for you, and we are going to work through them and show them the steps that I would recommend on how to tackle these until you get really, really comfortable with them. We're going to use a similar setup to what we did with the density equation in our last set of videos for the last unit, where you are going to write down all of your variables and write down all of the information that the question is actually giving you. Because with all of these questions, they're going to give you all of the variables except for one, and you can use everything else to solve for that one missing variable. Example 1. A 50-gram sample of an unknown metal. It says grams, so that is absolutely our mass. And let's go ahead and label it with grams. Is heated with 800 joules of energy, and energy is your Q. Do pay attention to those decimal points that they're putting at the end. They're giving you extra significant figures with that. If the temperature of the metal increases by 41.6 degrees Celsius, what is the specific heat of the metal? It's increasing by 41.6 degrees Celsius. It doesn't matter if we're in Celsius, it doesn't matter if we're in Kelvin, because our equation uses the change in temperature. So if you were in Celsius or Kelvin, it doesn't make a difference here. And so obviously we're looking for C, and the question ends with what is the specific heat of the metal? And remember what specific heat is. It's how much energy is required to raise 1 gram of this substance by 1 degree Celsius. So here we go. We're going to rearrange our equation, Q equals MC delta T, to solve for C. So let's manipulate it. If I wanted to isolate C, as if I were solving for it, I'm going to divide by everything that is not C. So I'm going to divide by m delta T, and what you do to one side, you have to do to the other. Now we have the proper organization of our variables, and now we just got to plug and chug our variables here. And now the only way you're getting it wrong is if you're plugging it incorrectly into your calculator. And let's make sure we're going to round to 2 sig figs at the end because our least amount of significant figures in all of our measured values given is 2. So let's plug this into the calculator. And we get, if we're going to round it already, 0.38, and then the units for this are a combination of all the units we used to get there. Joules per gram degrees Celsius. That's example 1.
Let's take a look at the other 2 calorimetry examples that we're going to be solving on the board here for you today. Example 2, how much heat does it take to heat 100 grams of water at 0.0000 degrees Celsius to its boiling point? I pulled this directly offline. What's the point of saying 0.00 degrees Celsius? There's no significant figures present here. Keep in mind, whenever you're rounding your answer to the correct number of significant figures at the end, only the measured values contribute to that. And so specific heat, for example, which is a constant, it is an intensive property, depending on the substance that you're looking at, is not going to contribute to your sig figs because it's not a measured value. It's a fact. Just like there's always 12 inches in a foot. That doesn't ever change. So the only thing that has significant figures here is the 100 point grams. So whatever our answer is going to be here, we're going to round that to 3 sig figs. 0.00 degrees Celsius, I guess they're just trying to emphasize the fact that we're straight up at the freezing point and we're going to the boiling point. But we're starting with liquid water the whole time as well. Example 3, what is the final temperature of a 76.4 gram sample of iron? Specific heat 0.444. If it starts out at 50 degrees Celsius and absorbs 11.1 kilojoules of energy. The biggest kicker here is the kilojoules of energy. Keep in mind, look at your units for specific heat. It's joules per gram times Kelvin. And yet the energy that it absorbed is kilojoules. If these aren't the same, you're not going to get the right answer if you plug it straight in. You have to do a little bit of conversion using that dimensional analysis we learned last unit in order to get the correct answer. So when we're solving it on the board, we're definitely going to make that one of our first primary objectives.
Example 2 reads, how much heat does it take to heat 100 grams, 100 point grams, of water at 0.00 degrees Celsius to its boiling point? So all that you need to internalize there is what is the boiling point of water? Well, it's 100 degrees Celsius. If I'm going from 0 to 100, then that is a temperature change of 100 degrees Celsius. And the way they've written this here, there's not really any measured values here. It's essentially saying from freezing point to boiling point, melting point to boiling point, whatever you want to call it. And so not really any measured values here, therefore it's not going to actually contribute to our significant figures here. The specific heat of water, which is a constant, specific heat of substances is an intensive property, doesn't change, is 4.184 joules per gram degrees Celsius. All right. So everything is what we need here. We're looking for the amount of energy that this water is required to absorb in order to achieve this temperature change. And the equation is already solving for Q as it is written. So really all I got to do is plug and chug. This is the easiest type of problem I can solve for here because it is straight up just multiplying them all together. And the only measured value here is the mass of the water. So that is going to make our answer required to be rounded to 3 significant figures here. We get an unrounded answer of 41,840 joules, but if we're going to round that to 3 sig figs, then it's 41,800 joules is our final answer. Let's take a look at example 3. Example 3 is, what is the final temperature of a 76.4 gram sample of iron? So notice what I'm doing here. As I'm solving this problem, I'm writing down the information as I receive it. Just match up the variables with the variable that you're looking for, the units to the variable that you're looking for. And the iron specific heat is 0.444. If it starts out at 50 degrees Celsius and absorbs 11.1 kilojoules of energy. So this question is not actually asking for the temperature change, it's asking for the final temperature. And remember, change in anything is actually just the final minus the initial. So essentially what we're going to do is we're going to use the variables that they provided for us to solve for delta T, and then use that delta T to solve for the final temperature, because it did give us an initial temperature of 50 degrees Celsius. Like so. So we have everything we need, except for there's one problem. This is kilojoules and this is joules. So as of right now, our energies are not speaking the same language. So what I'm going to do is I'm going to convert these kilojoules to joules, which means I need to multiply this by 1,000. And that's using that metric system dimensional analysis that we learned last unit to convert this to 11,100 joules. All right, so now that we've converted this to 11,100 joules, we're going to plug this into the equation. We need to solve for delta T. So if we're rearranging this equation, we're going to divide by everything that is not delta T in order to get delta T. And at this point, now we can plug in chug. Make sure you use that newly converted joules value, 11,100. And we get a delta T of 327 degrees Celsius. So the temperature changed by 327 degrees Celsius. And I guarantee if this were a multiple choice assessment, quiz, or test that you're taking, that this would be one of your answer choices. But you have to make sure that you're paying attention to what I'm actually looking for. I'm not looking for delta T, I'm looking for the final temperature. And so now, if delta T is equal to the final minus the initial, I can solve for that final temperature using the value that I just calculated. So delta T is 327, which is equal to TF minus that 50 degrees Celsius that they have given to us in the problem. And so we're going to solve for that very quickly. Simple algebra. Final temperature is 377 degrees Celsius. Let's write this in big, big font down here.
So now that we've just learned how to calculate how much heat is transferred within a reaction, now let's learn how to classify them. And we've got the two final terms of today, two final terms of the unit. Exothermic reactions versus endothermic reactions. And if we break down that word into word parts, we can probably define it before we even read the slide on the page. Exothermic. Therm is obviously heat, and exo is on the outside. So if I'm breaking this down, it's heat going to the outside, heat being released. So what this reaction is going to feel like to you is you're going to feel it get hot. The heat is being released. And so now, where's this heat coming from? This is the difference between what is called the system and the surroundings. And if you're ever observing a reaction, you are in the surroundings. The reaction itself is the system, and you can never, no matter how close you get your hands to it, you can never get your hands on the system. Okay? Get that through your heads. You can never get your hands on the system. You can only ever feel what the surroundings feel like. Okay? So if it's an exothermic reaction, we can feel the heat being exuded from it. Well, where's this coming from? Well, how it works in a chemical reaction is we are always breaking bonds and we're also making new ones. And how does it work? Well, imagine this is a bond. If someone was coming to rip these two apart, what do they have to put into it? They have to put energy in to break this bond apart. Therefore, when I'm breaking bonds, I have to input energy, but when I'm forming new bonds, the chemistry is released. When I'm forming new bonds, energy is released. So in an exothermic reaction, the energy that is released from new bonds is greater than the energy spent breaking the old bonds. So what is this going to look like graphically? Well, if I'm releasing energy, then the energy of the reaction is going to end with less than what it started with because it's releasing it, right? And what that means is that it has a negative delta H. Remember, delta H is change in enthalpy, the change in the heat. Because the reaction is losing heat, it has a negative delta H. Okay? So what would the graph look like? Well, it's going to start high and it's going to end low. So this is a graph tracking the potential energy at every point during the reaction. And so we're starting here and we're ending here. What is this hump that we have to get over? every reaction has a very steep slope at the beginning. And the reason for that, think of it like a toilet, okay? If you just flick the flusher just a little bit, not putting any pressure on it, just flicking the handle, it's not going to do anything. You have to go past a certain point, and once you go past a point, it's a point of no return. This is your toilet handle. You can only flush this reaction once you get over this hump. So you have to put in a little bit of energy to get over the hump, and then the reaction can proceed. Okay? So what would the energy be like if we were to reverse this reaction? Well, it would be the exact opposite if we just flip this graph. So then the activation energy would be from this point to the top, and then it would end here, which is exactly what an endothermic reaction is going to look like. In an endothermic reaction, it feels cold to us. Why does it feel cold? It's because the reaction is absorbing the heat energy. Endo, in, therm, heat. The heat is going into the reaction. And if the heat is going into the reaction, the heat is leaving the surroundings where we can feel. Therefore, it feels cold to us. So, the heat is being used to drive the reaction. And because it's absorbing that heat energy, it is a positive delta H. So endothermic reactions have a positive delta H, and exothermic reactions have a negative delta H. Even more so, if we're going to talk about this even further with our exothermic reactions, how it works is if we feel it getting hot in an exothermic reaction, then the reaction is starting to feel colder. It's releasing that heat energy, therefore the system is getting colder. It's weird. We can't feel it, yet it's happening. And in an endothermic reaction, the system is absorbing the heat energy, therefore the system is getting hotter, but what we are feeling on the outside is actually getting colder. Kind of weird. What is this one going to look like graphically? The exact opposite of our exothermic reaction. And I pulled this directly off of the internet. Don't mind the products typo here. It's direct Google image. I promise it's not my fault. But either way, notice that we're starting low and we're ending higher because the products have absorbed this energy. The reaction has absorbed a net amount of energy. As our final talking point of today, let's look back at our phase changes. Our phase changes, yes, are physical changes, but they are an exchange of heat, a transfer of heat. So which way are they exothermic and which way are they endothermic? That's the question. Well, let's just start with our ice cube here. We throw this ice cube out onto the front yard, right, and it's going to melt in the sun. Well, what is that sun doing for it? The sun is beating down on it, providing heat energy, and the ice cube is absorbing it. What does it sound like when something is absorbing energy? Well, that is certainly an endothermic reaction. It is absorbing that heat energy and is using it to melt that solid. So melting is an endothermic reaction. And what is it if I'm going from liquid to gas? If I'm boiling this liquid, it's the same thing, right? You put it over the stovetop, the heat is going into it, the water is absorbing the heat, and it is using it to propel it to the gaseous state. So if those are endothermic, then that means the opposite direction are exothermic. But that's kind of weird to think about. Liquid to solid, when something is freezing, it's an exothermic reaction. And you're thinking, but it's getting colder. How is it exothermic? It's getting colder. Yes, we feel it getting colder typically when we're freezing it because everything else is also cold. To freeze something, you typically put it into the freezer, right? But what it's actually doing is that kinetic energy within those molecules going from liquid to solid is leaving the molecules. The kinetic energy is being released because remember, towards the very beginning of this unit, solids have the lowest kinetic energy, liquids are in the middle, and gases have the highest. So for a liquid to become a solid once again, it has to lose kinetic energy. And where is that kinetic energy going? It's being released. It's being released as heat energy. So one final conversational topic of the day. Congratulations, you are now a citrus farmer. You own the second largest orange grove in all of Texas. I have the largest. And it's going to be a deep freeze tonight. It's going to get to -3 degrees Fahrenheit. Oh my gosh, we've never seen temperatures like this in the last 70 years. But you, as a very knowledgeable citrus farmer, because you studied chemistry intently, just before you go to bed that night, you go outside to all of your trees and you hose down all of your fruit. You hose down all of the oranges. And you do this because you know it will keep them alive. Why the heck do you do it? We'll give you a second. Time's up. Why do you do it? Isn't the water just going to freeze and into ice? And ice is cold. It's going to form a nice warm ice blanket? No, that's not why. Yes, you are watering, you're hosing down the fruit, knowing that the water will freeze, but that's what you want. Why? Because when water freezes, it's going from liquid to solid. And what did we just say? What type of reaction is that? That is an exothermic reaction. And if the water is freezing, causing the heat to be released from those water molecules, where are they going to go? Where's that heat going to go? It's going to go into your oranges, and it is going to provide it the heat, the warmth that it needs to survive through the night. Very cool. Chemistry. Chemistry. Have a nice day. See you next time for Unit 3. Atomic structure. Stay safe. Wear a mask.